Okay, great. So it's my pleasure to introduce today's speaker. Jerome Neufeld is a professor here both in DAM and also in Earth Sciences. And I just found out he's from Canada, from the university that we used to be competing with Toronto. So despite that, I'm still happy to have him here. Thank you so much for coming and look forward to your talk. Thank you.
Now, there we go. Now you get out. That's again. Good. All right. Great. Thanks for having me here to chat. I'm going to present, as it were, two topics, which really, in both cases, are how do I build a fluid dynamical model of flow in both cases, which is effectively in a porous medium, but one where really the structure of that porous medium is unknown. And in one case, it has to do with how do we understand how ice sheets move. And so how the water gets routed underneath the ice sheet is a critical piece of how we understand the response of ice sheets to climate change and, in fact, their natural variability. And the other one is, so that's sort of understanding climate change. The other one is a technology to try and take CO2 out of the atmosphere and put it underground, where the idea is for it not to essentially ever get back to the atmosphere. But again, there's a question about how do we understand where the CO2 goes when you inject it underground. It's very sensitive to the heterogeneity, to the structure of the rock, which there's no hope of getting enough data to constrain until you put the CO2 in. So the question is, how do we start to build fluid dynamical models which we can solve and then try and sample that uncertainty space? I should say it's more fun if you ask questions along the way. So I don't actually care if I make my way all the way through the talk. Just stop me and ask and we can discuss. And I'm going to try and also provide some context, which will give maybe more, things to chew on. So I've intentionally included a bunch of pieces of data that we can then think about. So this really doesn't need much introduction, but let's do it anyway. So the top left, you've all seen, I presume, that's the CO2 Keeling curve, right? And so from that CO2 Keeling curve, which is still precipitously rising, we get things like the temperature anomaly curve, which is also precipitously rising, right? For ice sheets, the real question is both the radiative balance of the Earth, but then what's the risk to sea level rise? So as we melt Greenland, Antarctica, the world's glaciers, we're adding a lot of water mass in the world's oceans. And so this is, as it were, the sea level rise over the last couple of decades. And you can see that thermal expansion, so just the heating of the ocean, has played a substantial role, but the added mass from Greenland and Antarctica and the world's glaciers is also quite substantial, right? I'll come back to this in a second, but here is the graph for Antarctica and Greenland on the same scale of the mass loss over time. And there's all sorts of interesting questions, I think, in this data. You can already see that there's definitely an annual cycle in the mass loss, right? And that we've lost thousands of gigatons of ice from both those large ice sheets.
So are these mass losses measured through gravimetric analysis or?
Indeed, absolutely. In fact, so here they are. In fact, I think, yeah, let me do it this way. Okay, so let me give you some context to how we understand the mass loss in Antarctica and where it's losing that mass. So what are the things that we can measure? We can now measure the bed topography. Bed topography, so where's the base of the ice? Where does it contact the rock? That's an interesting problem in and of itself because you can't see the bed. So what's really being done here is a whole series of radar flight lines, which then need to be stitched together. Current best estimates of how you stitch them together are to run a full Stokes simulation of the ice and use that to constrain the interpolation for the bed. So that's a product called Bed Machine, and it gives you a pretty decent estimate of the topography of the ice or of the ice bedrock interface over all of Antarctica.
Can I ask what's the wavelength that you use for penetrating the ice?
What's the, you can, I'm not sure if I know off the top of my head what the wavelength is. I think it's gotta be something like, I don't know, no, I'm not gonna think of it. Yeah, there are different ways. You can either do flight lines, so that you're at sort of hundreds of meters elevation, or in detail, they do towed behind snowmobiles or stationary radar. So you sort of depends on what the application is as to how precisely you're going to get a measurement, but then it's the spatial interpolation at the sort of content scale that's the issue. Okay, so that involves an interpolation. Here's the ice thickness itself, so that's essentially the top surface of the ice sheet, plus a few mountains poking at the top. And then from satellite measurements, you can reconstruct the velocity field of the ice over Antarctica. This is a logarithmic scale, albeit in the color contour, right? And so you see the sort of the broad pattern is very slow in the middle, fast flowing on the edge, really fast flowing on the ice shelves, but that's because these are floating over the ocean, so there's no drag from the bottom, right? So actually, when we're thinking about Antarctica, the real question is what's happening at the bottom of the ice sheet. How do we think about that subglacial condition? Because that tells you how slippery the ice is. So where the ice is floating, there's no drag from the bed, so it can flow a lot faster. And that's why you see high velocities in the ice shelves. Where it's on land, it's slower, and along the margins, where it's got a temperate base, where the bottom is essentially at the melting point, that's where you get these high velocities. This is also where you have the highest topographic gradients driving the flow. Right. The other thing, which is the real reason why people worry about Antarctica, is that if you look at the bed topography, most of eastern Antarctica, which is about half, is got a bed topography which is above sea level. A huge swath of West Antarctica has a bed topography which is below sea level. The sea is still not in there because you've got a thick enough ice sheet on top displacing the ocean. But you can already anticipate that potentially an unstable situation. Right. So now we come to the gravity anomaly. So here's the gravity anomaly. So you fly paired satellites, GRACE or GRACE follow-on mission, which essentially use interferometric, use a radar signal to figure out the separation between those two large masses, and as they fly over the Earth, they can measure the relative acceleration and work out the gravity anomaly. If you do that as a function of time, you can work out the mass loss. So the leading order signature from Antarctica is, like broad brush, Eastern Antarctica is not really losing mass. I mean, it is, but not massively. Western Antarctica is losing a lot of mass, right? And the key question here is, why is Western Antarctica losing a lot of mass? Well, it's at least correlated with sea surface temperature. So here's a picture or a map of sea surface temperature, and you'll see that around much of Eastern Antarctica, sea surface temperature is still cold as you get right in next to the ice sheet. And that's not true in Western Antarctica. So the key question with Western Antarctica is, how is this warm water giving rise to this mass loss? Right? And just to pose that puzzle in a slightly different way, for the ice shelves, they're already floating on the ocean. Right? So it's like an ice cube in a glass of water. If you melt that ice cube, you don't change the water level. You only change the water level if you either float a bunch of ice or you melt it and you take the water out. And so that's got to be the answer here. So the fact that you've got warm water up against an ice sheet is important, but it's important because it increases the mass flux from the grounded ice into the ocean.
So the mass loss map gain here is purely the absolute mass loss gain, not the flux.
It's the absolute.
The absolute, right.
Yeah. And you know, so this will become, I think, clear in contrast with Greenland here. So Antarctica is relatively cold on the surface, so you don't get a huge amount of melting on the surface of Antarctica, which is why it's the ocean that's the key driver, not the atmosphere. That's not maybe true right up on the peninsula where you get to higher latitudes, but certainly for the rest of the continent, you don't do a lot of surface melting, which raises the puzzle that I've warmed the ocean. I can certainly melt ice shells, but that doesn't change the mass budget. It's really the warm water getting in underneath the ice that increases the mass flux. So that's an inference, which isn't in this data, but that's sort of because you're not doing a lot of surface melting, that has to be part of that story. Well, let's do the compare and contrast with Greenland. So can do the same sort of piece of data analysis. So here's the surface topography. Greenland is different in the sense that most of the Greenland ice sheet doesn't actually flow out onto the ocean. So you get lots of pictures of outlet glaciers in Greenland, which do, but you can already see that most of the perimeter of the Greenland ice sheet is on land, right? So it's a different story. The ocean isn't actually getting in underneath much of Greenland. We can look at, in the same way, we can look at the bed topography of the Greenland ice sheet. And there's an interesting solid Earth question, which is also relevant, but on longer timescales. You've got that much ice, it's 3 kilometers in the middle, it's pushing down the middle of Greenland. So actually the middle of Greenland, the land surface is below sea level, but that's because you're pushing down on a sphere with a rather large mass. And if you're from Canada, then Hudson's Bay is still going up because of the loss of the last ice sheet, as is Scandinavia. Right, so here's the ice thickness, sort of 3 kilometers in the middle, going up towards the edge. And now if we look at the mass loss, so this is the same Grace gravity signal. Greenland is melting, and Greenland is melting basically all the way around the perimeter. So Greenland has a signal where mass loss is more or less uniform around the perimeter. And here's the same sort of logarithmic velocity scale. So you're feeding a lot of ice towards the edge. It's flowing fastest at the edge where it's where the topography is steepest. But here the story is that you're melting the surface, and that surface meltwater is getting to the base of the ice sheet, and so you're really lubricating the flow of the ice. So there's sort of two contrasting problems to understand. In Greenland, it's how does that surface meltwater make its way to the base and lubricate the ice sheet? That's really the dominant signal to climate change for Greenland, because it's feeling the atmospheric temperature changing. Whereas in Antarctica, it's really the world's ocean temperature changing that's driving the change. Both rely to different extents on how do you understand the subglacial hydrology, how do you understand how water gets rooted underneath the base of the ice sheet. So part of that question, well, you may not be able to see here. In the summer season in Greenland, you get about 100 kilometers worth of surface melt on the surface of Greenland. And that ice sheet has its own topography, and so you get what are essentially lakes and rivers on the surface of Greenland forming that look something like this. So here are surface melting leading to lakes. They're connected by little streams. Those little streams flow across the surface of the ice, and invariably they tunnel to the base of the ice. And that's for a number of reasons. They'll find imperfections in the ice, they'll find crevasses. There's also a feedback in the sense that if you have a fast-flowing river on land, right, that river will mechanically erode the base of the stream. The same thing is happening in Greenland, but actually with a different mechanism. So as you collect this water and it flows into the streams, you're getting a fair degree of turbulence. Right? And turbulence means essentially dissipation that goes into heat. You've got a body of water in contact with ice. That heat gets absorbed in melting the sides. So actually, as you collect the water in the streams, you also tend to have streams deepening on their own, basically through melting of the ice through which they're flowing. All of that gives you a mechanism whereby surface melting of the Greenland ice cap heads its way to the base, and that's how it lubricates the base of the Greenland ice sheet. Okay, we're almost getting to the kinds of puzzles that I'm interested in trying to solve mathematically. Let's at least see on a sort of a more detailed level a case study for how that meltwater actually impacts the flow of the ice. So here is a study by Fitzpatrick et al., where they were looking on the west coast of Greenland at something called Russell Glacier. And so they're looking at this glacier all the way up towards the terminus, and they're looking at the velocity, satellite-derived velocity of the ice, and an estimate of the melt rate. So the melt rate is the sort of the pinkish bars at the bottom here. So that's sort of onset of the melt season and forwards. And this is looking at the bottom of Russell Glacier, the middle of Russell Glacier, and the top. So higher elevations at the top, lower elevations at the bottom. Here's the puzzle, and it's not a puzzle that anybody really knows the answer to yet. I want to use it to sort of highlight the kinds of questions we'd like to ask and answer. In red and blue are the velocities measured in these three chunks. And in pink behind is the melt rate. So you'd expect that the melt rate would go up and the sliding speed would increase because you've now lubricated the base. Well, actually what happens in all three cases is the melt rate turns on, the sliding speed increases, so the ice starts moving faster. And then while the melt rate is still increasing, the sliding speed starts to decrease again. And so that tells you that underneath the Greenland ice sheet, something is changing in terms of how that water is communicated around. And in particular, we think that it's the water pressure that really essentially lifts up the ice sheet and allows it to slide. And so the question here is, as you put more water down, at first you make something that's analogous to, I don't know, the swamp of the Fen, Bighorn Fen, if you've ever been there, right? It's broadly lots of water. And so that's lots of water evenly distributed, the ice can slide over that. As that then develops, as you add more melt, you can now channelize and melt, as it were, little rivers at the base of the ice. Those rivers are very effective at removing the water. And so the average water pressure can still decrease even as you add more melt water to the surface. So now, if you're asking a question on a sort of a glacial length scale, so on the length scale of the thickness of the ice, which is about 1 kilometer, you need to ask, how do I think about modeling the flow of that water when the flux and its spatial dependence can vary through the melt season? So that really is the sort of the challenge that I'm working towards, is how do we think about an evolving porous medium where we know that it's got to evolve to understand these kinds of signals over time? What kind of data could we use to constrain it, and how would we test that sort of model?
So with a kilometer of ice, wouldn't there be like a change in the kind of, I mean, the pressure must be so high. You know, does that change the structure of how water behaves, or?
It will change the melting point by about a degree, but
Okay.
other than that, no, it's still, as it were, regular water.
I mean, I know water is an incompressible fluid, you know, but
More or less.
more or less. I mean, but even that kind of pressure, you might expect that something's happening. I don't know.
So the pressure is well, you're kind of that slide next. I think the pressure is mostly important because it either jacks up the ice off of, you can imagine you've got a rough topography, and as you increase the water pressure, that ice is contacting less and less of that rough topography. So that would be one. The other, so that's, as it were, ice sliding over a hard bed. The converse, which has almost the same effect, is if you think that ice is sliding over a distributed till or sediment, which is likely the case because it's eroded much of that landscape, then even that granular till will also behave differently with water pressure. So when you're at the beach and you've got wet sand versus drier sand, the wet sand you can move really easily, the dry sand less so. And that would be, that's sort of where you think that the water pressure plays a role subglacially.
Okay.
Or at least that's the current thinking. Yeah.
So if I understand correctly, you're suggesting that when there's a little bit of water, it's kind of thin film that allows it to slide easily, but when there's more water, there are some rivers that creating that effectively drains the water. And so, and that's happening all underneath the ice sheet. Does that mean that the erosion is happening underneath the ice sheets?
So there should be erosion of sort of so yes is the short answer. There should be erosion of two types. So this, I mean, this is obviously on the surface, but you can see that that flow of water has already eroded the top surface of the ice. The difference at the bottom is that you can do erosion in two ways, right? You can erode the granular, the sediments. You can also erode, just like you've done here, you can melt out the ice. So those are called Roethlisberger channels. The difference at the base of the ice sheet is that because you've got that kilometer worth of ice, and you know that on a 2-week or longer timescale, ice behaves like a viscous fluid. If you've got a river flowing through, you can melt that open. As soon as you decrease the water flux, the ice will creep back closed. So, part of this story is that at the end of the melt season, it does not take very long at the bottom of the ice for all of those cavities that you may have melted open to close back in. So that would be why you'd expect if you formed a river network during the melt season, it's going to definitely be closed by the time you get to the next melt season. What's that? Excellent question. I mean, yeah.
Could I ask one more question? It sounds like as you're describing it, as it melts at the surface, it then kind of goes down to the base and then kind of exports. Are there any dynamics within kind of the main body of the ice sheet that it moved outwards?
So A, we don't know. B, you have to be completely crazy to try and get the data to understand this question.
Yeah.
Part of the reason why this is difficult is because the channels that you form are probably at the meter or thereabouts level. You can't see them with most remote sensing techniques.
Okay.
You know that they're there because you can put, for example, dye tracers into these surface rivers. And the trend at time to the end of the ice sheet is far too fast for anything other than a river. So you know that they must exist, but you can't, as it were, see them directly. The you must be crazy comment is there are some people who have, for moulins like this, once the water stops, if you're crazy and quick, then people will rappel down.
Oh.
There are some maps down to about 200 meters into the ice, but
Okay,
it's
so
crazy.
they rappel down and they look at like where all the all the different channels down to 200.
Yeah, so I mean, the old picture of these moulins is that they would channelize straight to the base, just the hole.
Yeah.
Right, and some of them probably do that.
Yeah.
And I'll show an example in a minute, which is definitely that.
Yeah.
But there are some examples where people have rappelled down, and it spends some non-trivial time making its way through the middle of that kilometer of ice.
Yeah. But because I can imagine the same way that it's finding imperfections in the ice crevasses, it could find that in the depth-wise layer as well.
Yeah,
And you could put a drone down. Why send a person?
Yes, and I think you probably needed the cavity is not so large that it's sort of like, can you send a drone through a cave?
Yeah, you can.
Which you can, right? And in fact, if you're interested afterwards, I'll pull up the paper. There is somebody who's flown from the terminus of a glacier a drone up, so that that has been done, but just not in great amount of cases.
The other thing is, if these rivers, couldn't you do a thermal imaging of the coastline and see where you have these, cold streams coming out and then work backwards instead of where it is coming from?
People do map the flux of water.
Yeah.
It's all basically at 0 degrees because it's gone kilometers in contact with ice. So even if it's melting that open, it's essentially turbulence with water at basically 0 degrees. If there's any heat generated, that goes into melting rather than changing the water temperature.
How about like the difference in salinity?
Quite important actually. So in terms of for Greenland, and in fact in terms of Antarctica, ice melts for 2 reasons. One, it's hot, you get it hot. 2, you get it salty. I mean, they're basically doing the same thing. Salt decreases the freezing point. So if you started at 0 degrees, you add salt, then all of a sudden the freezing point is -2 at ocean salinity. So it's got to melt, dissolve. So certainly in Greenlandic fjords, the flux of meltwater plays a key role in setting the local salinity of the fjord, and that definitely plays a role in the meltwater. So absolutely. And similarly, people are starting to think about, just like we do for coastal aquifers around the UK, for example, as you draw water out of coastal aquifers for drinking, you've taken the fresh water out, the salt water from the sea intrudes. Well, the same thing is happening on the ice sheets. So that flux of salt water under the ice sheets is potentially also a source of melting. Let me give you another example. This is from a group at MIT. Actually, Laura Stevens is now a professor in neurosciences at Oxford. And what they did was they went and deployed 13 GPS stations around one of these lakes that form on the surface of Greenland in 3 successive melt seasons. I'm showing you the movie from 2011. I'll explain this in a second, but you've got these 13 GPS receivers. There's a moulin at the edge of the lake. The lake is roughly 10 square kilometers. And what they measure is a catastrophic drainage event. So this lake, 10 square kilometer lake, drained in about an hour and a quarter. And they measure the response with this GPS network. So this will play over again. And what you're seeing here is essentially an inversion for the uplift at the base of the ice. So this is surface GPS measurements of the vertical displacement interpolated to the base of the ice sheet. So that's the vertical motion. The horizontal motion is the extra basal slip. And then this is an inference for a fracture that formed across the lake. And so the sequence is essentially the lake filled until water went through this moulin. That started to lubricate the base. The ice essentially got lubricated differentially and so tore itself open. All the water went down that fissure. And you can see the bubble of water because the ice is popped up. And you can see that I add this much water and I start to lubricate the base and the ice starts to slide, right? And at least from a, mathematics, physics, computational standpoint, this is kind of like doing the Green's function approach to adding meltwater. I know I have a 10 square kilometer lake. I added at a point in time. Now I can look at the response, right? And so that's, for me, this is one of the ways that we can start to think about how do we calibrate both where does the water go and what does that do to the sliding speed. So part of how we've and I'm just going to give you the barest flavor of this. Part of how we've thought about this problem is to treat the ice like an elastic surface, because on timescales of less than 2 weeks, ice responds elastically with a subglacial till, which we've treated as a porous medium. In this case, we thought about it as poroelastic, so there is some compressibility to the water and to the till. And then we've asked the question about, okay, where does that water go? This is like a fracturing problem because it's so quick. You've got this lake that's just drained and it's flowing out, and we'd like to understand where does it go so that we can now correlate that transient water pressure with the observed speed. The kind of thing that you end up writing down is flow driven by pressure gradients, either in the porous medium or in the gap that opens up. And the pressure is a combination of gravity and elastic bending of the ice and the squishing of the till. And here's the kind of solution that you get to this kind of problem. So this is, as it were, just for a radial spread as you inject water for a given amount of time and then stop. And what you find is this ends up looking like a blistering problem. So if you've ever tried to peel tape off the table, the rate at which, if you stick the tape to the table and then pull, the tension in the tape is the thing that causes it to delaminate, but it's the process is right where it comes off the table that determines how quick that spreads, and that's the case here. It's the process of sucking water into the tip of this fracture that really determines how fast that blister expands. And we can start to look at how does that compare to the GPS signals. So this is one of the GPS receivers here, the vertical deflection over a whole number of days. And what you can see is this is pre-drainage, that's the lake really drained. And then this is the period where you've got a finite volume that lake is underneath and the blister is slowly spreading compared to a model that tries to understand that spreading. The challenge here, and I might We'll see if I get to it. The challenge here is that all of the properties subglacially can vary as a function of time and space. And so how do we start to make computationally efficient estimates of the water flow so that we can span that parameter space? Here, let me switch back to Antarctica now, because I've shown you, as it were, the observational Green's function approach. Let's now go back to Antarctica. So here's Antarctica. We're again now going to think about the grounding zone, but in particular, I'm going to look at it at the Rutherford ice stream, which is up there. And let me introduce it with the following data from Brent Minshew's group at MIT. So Brent took INSAR satellite data from the Rutherford ice stream and essentially took 3 years worth of data and restacked that data according to when the snapshot was taken within the tidal cycle. So in this case, the predominant forcing is ocean tides. And so you're seeing essentially a movie of the tidal cycle, which has been recorded over 3 years, but all put into the same 2-week period. If that makes any sense. And I'm showing the two components. So this is the vertical component recovered from that INSAR image. What you see is the Rutherford ice stream flowing from the top left to the bottom right. This bits over the ocean. So this is floating ice, that's grounded ice. So it's sitting on the bed. And this wiggly line is the inferred grounding line, right? And so the ice is going up and down with the tides, the center line. And you can slightly see the wiggle progressing inland as it grounds. But that's the response to the ocean tides. So that's going up and down twice a day. Here's the puzzle. So here's the horizontal speed of ice of the Rutherford ice stream. It's a so-called ice stream because fast velocities fairly narrowly confined, right? And that's the mean velocity. If you subtract the mean, you get this signal, which pulses every 2 weeks. So tides don't force at 2 weeks. You have tides from the sun and the moon, and the beat frequency has a 2-week period, but that's a beat frequency. It's not a primary forcing. So why is it that the ice responds at 2-week time scale when it's being forced at 12 hours? Right? Where's the nonlinear filter in that? So the nonlinear filter, and I'm going to spare you the detailed model, just going to give you the sort of heuristic one here. The detailed model is essentially comparable to ocean waves on the beach. So when you're at the beach, you see the waves coming in, the waves crash in, and they come in very fast because they're thick as they come in, and so there's very little resistance. But as you're standing there, the waves just crash in over your feet. Now the swash goes back out. The swash takes a lot longer to go back out because as it goes out, it thins, and you're left with a thin film that's trying to drain over the beach. And there's lots of resistance to that. So now translate that to a problem in which you've got this elastic ice sheet sitting on top. As the tide comes in, you essentially fracture that ice off the bed, right? So that's a quick process. As the tide goes out, you have to drain all that water back out, and that process is slow, and you leave a macroscopic film behind as you do. And so there's a difference between the incoming and outgoing tide, depending on how fast you can drain the tide back out. And the speed of that would depend, for example, if the bed was really steep, you could drain that water back out very quickly. If very shallow, it takes a long time to drain.
Is the like on a beach, the bed is porous, right? And
Yep.
so then there's some level of like how saturated is the bed or whatever, how much is draining into the
Yep.
sand. Is it the same thing here or?
So the fact that the beach, before the wave might be only partially saturated, so there might be some air.
Yeah.
That's probably not relevant to the grounding line.
Okay.
So in that sense, the third phase, the air phase, isn't relevant. The fact that the gap is narrow is probably the more relevant piece. The physics, it turns out, is if you swap elastic beam for surface tension, the physics is the same as if you take your hand and you dip it into a bucket of water and you pull it back out. Your hand gets very wet very quickly as you go in. It takes a long time to dry off on the way out, right? Because you leave a film of water behind you. You know, you swap the physics, the surface tension, there's another phase, but that, I mean, effectively, it's that the resistance is a lot to the film flowing off your hands a lot greater on the way back out. Okay, so now let's think about the fortnightly tidal cycle. So if you essentially, if the grounding line goes inland fast on as the tide comes in, and then slow on the way back out, now you have a way to rectify the signal, which is the beat frequency of the tides. So if you have a really steep base, right? So if the film drains quickly on the timescale of the tides, then you'll just simply go in and out, and you'll see the 12-hour signal. If you're on a very shallow slope or a very impermeable base, a very porous base, then it could take a long time to drain out. So you go up fast with the tide, drain slowly, up fast with the tide, drain slowly. And that gives you a way of following the envelope of the tidal cycle. You know, in the most ridiculous end member, you just basically sit at the peak of the tidal envelope, because you wouldn't be able to drain back between fortnightly tides. And the reason why that's interesting is that if we go around the margin of Antarctica and looking at grounding zones, just to give you a sense, for many of things like Thwaites, the Doomsday Glacier has, I mean, it's a rather corrugated grounding line, but it is a very flat grounding line. So tidal migration in places like Radford or Thwaites or some of these other glaciers can be up to 10 kilometers. So between high and low tide, the place that you think that the ice should touch down might change by 10 kilometers, and that's a lot of distance and a lot of water being sucked in and out. So I'd argue that's an excellent way that we might communicate the higher ocean temperatures to the other side of the ice.
Why do you say it's a non-linear filter? I mean, a linear filter would do the same effect as well. I mean, first order Kalman filter would have the same exact behavior as what you show on top.
It's a good question. Okay. Fine. Yeah. Certainly the process that drives the flow is a nonlinear, it's effectively a nonlinear PDE governing that flow.
Right.
That's maybe purely from a signal processing.
Yes, signal processing, I'd say that's a first order Kalman filter. I mean, that's what I would.
Yeah, fair point.
Okay.
Okay. Anyways, to link it back to the ice flux, here's the velocity at places like Beardmore or Rutherford Glacier, which definitely, you know, these are two different end members which have, and were comparable slopes, comparable, well, we think it's comparable sediments underneath the glacier, but a different tidal amplitude. And in one case, you basically just recover the fortnightly signature in terms of the sliding speed. And in the other, you pick up both signals. So there's definitely some evidence that you can see both. And in some sense, for me, if we're trying to calibrate how we think about transient subglacial hydrology, this is like the Fourier approach. I know exactly the signal I'm forcing with. Now I'm trying to understand how does it respond. Okay. Before I'm going to do a complete switch now. Does anybody have any other questions about subglacial hydrology? There's lots of interesting, outstanding questions there. No. Okay. So if there's one takeaway, it's that understanding how ice sheets respond to climate is the big outstanding feature is how does the water get around at the base of the ice sheet? And it's really, it's basically one of these very data poor areas. We don't actually have direct data for that water. And so we need to make an inference. And in order to do that, we need to have some way of calculating both how does the water change in a transient fashion and in a spatial fashion. So that's sort of where we're headed. So let me take you to another application. This is also porous flow. So this is geological carbon storage. The idea has been around for a while. And essentially it's to take sources, typically concentrated sources of CO2, and instead of having them emitted to the atmosphere, the idea is you inject it in the ground, where you would like to stay trapped permanently. Right? And the challenge, well, there are a number of challenges, but one of the bigger challenges is as you inject the CO2 underground, CO2 is less dense than water, so it's buoyant, and so you need some way of trapping it there. And the classic ways of trapping it are you put it underneath some impermeable piece of geology, so you inject it underneath a mudstone, for example, and then as the CO2 rises, it'll be trapped by that structural trap. But there are other ways to trap the CO2. So for example, the analogy would be if you take a sponge into a bucket of water and you pull it out, of course you've trapped a lot of water in that sponge through surface tension. So surface tension will also immobilize the CO2 within the rock. And that's in the lingo, that's called residual trapping. And the second is that just like you can have carbonated beverages, CO2 can dissolve in water. And so if you dissolve CO2 into ambient water, that makes the water dense. And so carbonated water sinks. So that's considered another way to stably store it over long times.
Just a question about the carbonated water, but like it won't do the same as soda, like that it will stay in the water, or at some point we will.
It's
like
good question. Just like a soda bottle, when the company ships you the soda bottle, so long as you've got the cap on, the pressure in the bottle is still high enough, and the CO2 is in solution. Crack the cap, you release the pressure, you've changed where you are in the phase diagram, the CO2 dissolves. So a interesting natural example is in Colorado. Colorado has a lot of CO2 in the groundwater because it's got the Yellowstone hotspot underneath it, which is a natural source of CO2. So there's a lot of carbonated water there, and there are some groundwater wells which have been drilled, and there's a famous one called Crystal Geyser, which is basically a water well which was drilled down into what turned out to be a saline aquifer, but it's carbonated, and as the water flows down through that aquifer and up the well, it of course depressurizes, and the well geysers on something like a 6-hour time scale. So basically, you're forcing this carbonated water out, the bubbles come out of solution, it blows its top, and then it comes back. So absolutely, there's a question about, if you release the pressure, the CO2 will come out of solution. Typical injection is below 800 meters. So all commercial injection is 800 meters to just under 3 kilometers depth. And at those depths, yeah, CO2 is super critical, and it's under enough confining pressure, it's not exalted. So there's still, and I'm sure there will remain for many, many years, a question about whether we'll actually do CO2 sequestration at scale. And that's a question for the policy folks like David Reiner. Current thing, just to give you a sense, CO2 sequestration originally was viewed as a way to decarbonize coal plants. The best way to decarbonize coal plants is to shut them down. And that's more or less been effectively done in huge parts of the world, possibly excluding places like China. There are still a lot of parts of the economic chain where we produce a huge amount of CO2, and the characteristic ones are things like cement and fertilizer and steel. And so there are still places where we think actually the lowest hanging fruit is probably sequestering the CO2 rather than there's going to be some sort of spectrum of solutions. And then the fourth way is certainly there are companies now which do direct air capture, which is expensive and energy intensive. So you ask whether this is a reasonable way forward. But nevertheless, once you've captured that CO2 directly from the air, you still have to put it somewhere. And they all rely on something like CO2 storage. And just to give you a sense of both the scale and the action, as of 2020 or thereabouts, we were injecting something like 29 megatons of CO2 per year around the world at about it's just under 20 large-scale CO2 projects. So it's not a future technology. It's just it needs policy incentives. to actually be done. And those policy incentives, of course, would include something like a robust carbon cost. Yeah.
Talking about policy, I'm just curious, do you work with policymakers at all, or who translates your research findings, or help they arrive at the policymakers meeting?
So I think it was you who were talking about David Reiner.
Yeah.
So, I mean, in Cambridge, the person who has thought most about policy around CCS is David Reiner, both policy and public acceptance and that sort of thing. So yeah, and I mean, so I've worked with, I've given testimony to government on CCS. I've mostly focused on the sort of fluid dynamics.
Yeah, okay, so the pipeline was more academic, technical, you work on this, and then another academic and policy, like David Reiner talks to you, and then he talks to the policymakers.
Yeah, I mean, roughly speaking, yeah. I mean, I'll give you an example. Oh, here, let me skip ahead. I'll give you an example of sort of, or I'll frame this in the policy sphere. So in terms of CCS, things that have been tried that from a policy perspective have been miserable failures are sequestering CO2 underground, under the land surface. Miserable failures because people get very, there's a real public worry about CO2 sequestration. And so the most, the biggest sort of failure of a project was in the Netherlands, where they were, trying to start a project which was underneath people's houses, and people were just far too worried about that. There's an example from more rural Australia where, and I'll show some data from it, where it's not a large-scale injection project, it's more of a test project where they inject something like tens of thousands of tons in a go. But there they spent a huge amount of time essentially interfacing with the local stakeholders. So it's a research site, and in fact, the local farm owners are helping to run the research site. And for that reason, they have a much different sort of local interaction. In the UK and in other places, we sort of dodged this issue because any place that we might store CO2 is offshore. So, the way that the UK sort of resolves that particular question is, let's just put the CO2 in old reservoirs or in saline aquifers offshore. And to give you a sense of scale, we have I'm not suggesting we're going to do this, but if we sequestered all of our current UK emissions, we have 100 years worth of pore space. It's sort of a rough estimate offshore. Now, we're not going to do that, obviously, because that would, there's no way you're going to put all your eggs in that basket. But that's just to give you a sense of, there's a ton of space that you can put CO2 in, not underneath anybody's house. Yeah. The other thing to say, and this will become relevant, is there's a long-running site up in the North Sea. Here, I'll just switch to that, called Sleipner. And this is also, I think, relevant from a policy standpoint. So Sleipner is a project where since 1997, they've been injecting, I guess 1996, they've been injecting something like a megaton of CO2 per year underneath the North Sea. That's where we have some of the best data for how CO2 migrates. And from a policy perspective, the whole reason why this site exists is because the Norwegian government put a $55 a ton tax on offshore emissions of CO2. So previously, you would get natural gas out of a reservoir under the North Sea, you bring it up to an offshore production facility. Many of those reservoirs already have something like 5 to 10% CO2 mixed with the natural gas. So there's essentially a chemical plant on those offshore production facilities which separates out the CO2. And historically, and in many places of the world, this is still the policy that CO2 just gets vented to the atmosphere, which, in the modern day is just completely crazy. So $55 a ton was enough for the Norwegian company Statoil at the time, now Equinor, to drill another hole. And so now they take that 10% CO2 from the natural gas stream and they pump it underground. So I guess that's the way of saying, $55 a ton in 96 was enough for a company to invest to do a megaton per year. Now there's all sorts of questions in terms of, okay, but what about all the rest of this, CO2 associated with the natural gas you're bringing out? And of course, we want to incentivize decarbonizing things like steel and fertilizer, but that's sort of where the policy debate is focused with CCS is how do we provide enough financial incentives for this sort of thing to be feasible? Yeah. So I'll pose the next question. So, okay, so we've got, as it were, a megaton of CO2 being injected underground. And this is about 800 meters below the seafloor to something called the Northern Shale Formation. So that's a shale layer which is really rather impermeable, and it's underlain by about 200 meters of what is effectively beach sand. So just like water flows through beach sand, here you can inject CO2. This is a saline aquifer. So it's full of salt water, and that CO2 will displace the salt water and be trapped underneath. The other advantage here is that because there's this natural gas field, and the company wanted to see what was happening to the natural gas field, they took seismics, and so we can actually see where that CO2 spreads as a function of time. So seismics are a way of looking, essentially using something like sound waves deep within the earth. You typically measure it in two-way travel time, so the time it takes for the sound to go down, bounce, come back up. So two-way travel time should be thought of as depth. And this is what that region of the North Sea looked like before they started injecting CO2, and this is it afterwards. So just to sort of color that in, they started injecting here at the base of this 200 meters of beach sand, and that CO2 is buoyant and up it rose, and it starts spreading out. The thing that's tricky here, and just to sort of highlight this point in the CO2 context, you don't really get to see the structure of the porous media beforehand. The wavelength of the seismic surveys is about 10 to 15 meters. So anything below that is essentially invisible. And yet the CO2 is finding what are thin mud drapes within that rock and spreading out. And so you're really sensitive to heterogeneity. And the question is, how do you start to understand that heterogeneity in a way that you can start then getting some sense of where the CO2 will go? Just to say, there are about 9 layers of these mud drapes, followed by this top layer, then this huge layer of shale. The CO2, there's no evidence that the CO2 has gone beyond that. This is a sort of prime example of megaton per year, and the CO2 is not getting anywhere near the atmosphere. Megaton per year is small compared to anthropogenic emissions of CO2. So you need to scale up hugely. But as I say, you wouldn't just do this. Okay, so let me give you a sense of the kinds of things that we do. So if we're thinking about the CO2 spreading, it spreads over the space of kilometers. The plume is 10 meters thick at each of those layers. And so the minimal model that you could write down for that CO2 plume is effectively something that either spreads under its own buoyancy, so like a spreading drop of honey on the table, or something that runs upslope because it's buoyant, right? And the devil is in the details, so you have essentially integrated the flow in the porous medium over the depth of the current. And so all the heterogeneity goes into how you make that vertical average. So what's typically done from previous experience of other folks in the oil industry is they'll run a simulator which tries to solve for the flow in all 3 directions, right? And that is computationally fairly expensive. And it's really hard to capture these really thin buoyancy-driven flows. And so the approach that we've taken is to do this vertical average so that we can then do a simulation. So this is now a simulation where we're taking the known volume of CO2 that gets to that topmost cap rock. We're taking the topography of that topmost cap rock, which is what's in the background here. And then we're injecting CO2 and letting it rise and spread and find the top of that cap rock. It's sort of analogous to what people now do for flooding predictions. You put water on the Earth's surface, you have a high enough EM of the Earth's surface, you can then reroute the water. And actually doing that in a computationally efficient way means that you mostly care about just the thickness of the water. And that's the case here. Right? And the advantage here is that because we're data poor in the sense that we don't know the structure of the rock a priori, we'd like to sample a huge number of realizations to try and understand what's the sensitivity to the different heterogeneities in the rock. And with this depth average model, just to give you a sense, we can solve for 25 years of injection history in 2 minutes on a laptop. It takes something more like 24 hours to solve the same problem with a 3D reservoir simulator, where you have the grid space fine enough so that you can actually catch this thin buoyant layer of CO2 spreading. So there's really, or at least we think there's really some utility to trying to figure out the most minimal model that captures the right physics. And then what I'd like to suggest is there's an interesting conversation to have, and maybe you guys are interested in it, in either the glacial or the CO2 context. How do you take that minimal model where you know what your sort of the kinds of things, the heterogeneities that you're averaging over, and then efficiently sample the whole spectrum of space of the different kinds of heterogeneity within that reservoir? Or in the glacial case, how do you take a minimal model of the water flowing underneath an ice sheet and then sample it in an efficient enough way that you can start asking about the temporal and spatial evolution of that subglacial network? So that's really where we're heading. In this case, for example, with the CO2, it turns out that not only do you need the macro topography, but you need some heterogeneity, and this is just to say that we can span a spectrum space of what that heterogeneity might look like, because we've got this computationally efficient tool. Let me show you one last. Let's skip ahead. I've run out of time. Let me show you one last piece. So I said one of the things that might stably trap CO2 in the subsurface is surface tension. So you can imagine as this buoyant CO2 spreads through the rock, it's leaving blobs of CO2 trapped within the pore space, just like water gets trapped within a sponge. So you can also add that into these depth average models. And so here is comparing against seismic data from this Australian site, where on the left, I'm showing the amount of mobile, so still moving CO2. And on the right, I'm showing the amount of trapped CO2 that's trapped there through capillary forces. So again, our approach has been, how do we take the minimal physics, create a computationally efficient model, and now run it so that we can start spanning the spectrum space of sensitivity to heterogeneity, sensitivity to uncertainty in the measurements, and really going forward, how do we think about the sort of possible scenarios for that CO2? Okay, look at that, because I've run out of time and over time. Okay.
Thank you very much. We have time for a few more questions. Anybody in the audience or somebody online? You could just type your question in the chat and I can answer. I can't see it here.
Okay.
Okay, so I had a question. So, I mean, I think it's very interesting talk. I mean, I think there's lots of stuff going on here. Part where there's clearly some kind of resonances. We also do models, we do models with different things, forests or mostly forests actually, but the general idea of having what Gihan calls real systems, taking a real situation and then coming with a simulation model which mimics it to some extent. So we need to know what are the parameters, what are the features on which we must have a good match, what are features are not irrelevant, right? So that's one thing. And then you can do a lot of variation analysis in the simulation work, and then you send to real, come out again and say, okay, what do I want to see? So I think the parts which are interesting are to constrain the feature space so that it's useful, and then use lots of variations of multi-color type analysis to see whether it start, and then make forecasts of what you'd expect to see. And then from the error that you're going to see from the forecast to feed that back into the model, and essentially do like what you might use topography to say, okay, this is the point where I'm going to do the change in the model. So there's a way of thinking about it that is very computational. but might be useful to.
Yeah, no, I mean, that mirrors a lot of our thinking on this, but I mean, as with all of these things, it would be good to discuss further, just getting into the details. I mean, I completely agree, because in many of these cases, it's, you know, and I'm sure this is true of the forest case as well, it's it's almost a question about like, so what can you actually measure?
Yeah.
Because if you can describe what you can actually measure, then you can understand what it is that you could actually benchmark.
Right.
There's no use, well, at least in my view, there's less utility in modeling something that you couldn't then verify.
Exactly. Yeah.
Because then it's just
Right.
imagination.
So, I mean, one of the things that Ihan is doing is inversions of physical models. If you have a physical process model that says, given these parameters, you get this output.
Yeah.
We have a machine learning type approach that allows you to invert it and from the observations work back the parameters.
That would be really interesting.
So we have, as long as the process is deterministic,
Yeah.
then our approach is actually directly relevant here. So
Yeah, so that would be fantastic to talk in detail about that sort of thing.
okay, well, we will follow up. Are there any other?
And just a quick question
Yeah.
on the motivation for the like flow of CO2 in the second example.
Yeah.
And is the concern there that as it flows, it might find imperfections or something in like whatever the substrate that's trapped under, and then it might re-emit, or is it just a general question of how the CO2 is moving in these carbon capture, like geological carbon capture situations?
So the original concern was exactly the finding an imperfection in leaking.
Yeah.
And many years ago, I did quite a bit of work on exactly that question. I think the sort of the summary is, because you're injecting at either 800 meters to 3 kilometers depth, if you leak out of the primary container, as in, you leak past your barrier at a kilometer depth, you still have a kilometer worth of messy geology to make your way through.
Yeah.
And so the vast experience of most of these projects, in fact, I don't know of one that demonstrably has leaked to the surface, is that, even where it has started to migrate out of that initial container, it's not migrated far. So, be completely honest, well, let me finish that first question though. It's now really migrated to a permitting question. So, there's the question about policy. Are we as a society actually going to spend money on putting CO2 underground? That's a policy question. If we do, and in many places we are, then there's a permitting question. And the permitting definitely relies on, you promised to put the CO2 here, tell me how far it will go. And the tell me how far it will go is part of the permit. So it's essentially treated like a waste disposal. You need to be able to assure that it will stay within some bounds. If you want a worry, which isn't a worry in the North Sea, but if you want a larger scale worry with CO2, it's that there are, of course, going to be situations where if you inject it into a reservoir where there wasn't that much more room for the CO2, then all you're going to do is increase the pressure, and that looks a lot like induced seismicity. So in places where there isn't a lot of pore space available for the CO2, you could drive seismicity through injection. And that certainly has been a concern for CO2 sequestration. But again, in the context of the North Sea, that's not really an issue.
Yeah, and presumably even if it does make its way through the vertical structure of the geology, it would dissolve into the ocean, still take a while to leak back into the atmosphere.
Oh yeah, I mean, ironically, this is not really being considered in that way now.
Yeah.
In the early days of carbon sequestration, one idea was, well, let's just take a pipe from an onshore facility and go to sufficient depth in the ocean such that the CO2 dissolves, and then you just get dense CO2 saturated water. The problem with that is, of course, you've changed the pH of the water. Right. So, if you're worried about the bottom ecosystem, then this is not a great idea. Of course, at the moment, we are fully, completely acidifying the surface waters because, we're dissolving a huge amount of CO2 into the surface waters. So, yeah.
Thank you. Okay, thank you.